Okay, well, today's lab is spirometry, so I'm going to give a lecture, and the lab will confirm what we talk about today in spirometry. The spirometer measures changes in lung volume. The max volume of all the airways in an adult is about 5 to 6 liters. Respiratory physiologists have defined a series of volumes and capacities that are easy to measure with simple lab equipment. And we have the equipment here. And we use the BioPack, and it's all set up. You can measure these values today in 2 subjects, right? I have copies of the lab over there that was on Canvas. One should be normal, one should be quote-unquote COPD. If you have any history of respiratory issues, you don't have to share this information. You can just it's totally voluntary. But if it turns out you just have to have 2 normals, have 2 normals. The point is, let's have 2 subjects and see if there's a comparison. And what we have today is to calibrate the machine, we have these syringes, which basically just pump air. And by just pulling the plunger in and out, you simulate breathing. And the subject has this set up here. The main piece of equipment is being held in the hand. It's called the airflow transducer. I have the desk here. And one of these is at each thing, and there's a diaphragm that you can breathe across. And these are reusable, so students breathe through these. And so it's very important that you use a filter in between the airflow transducer and your mouth, because I always tell students for this time, this is the most important piece of equipment. Because if you forget to use it, not only will your values be off, you're putting your mouth right on here, and I don't know what's on there from the last time, because sometimes students forget to use these, and they breathe right on it, and all their germs are on it, and I don't know what's on there. So this protects you from it. It also protects your mouth germs from getting on there, okay? And so, again, this is very important. Don't forget to use it, and you'll be okay. And also, we're making the mouth the airway, so we have to use a nose clip. And then so you're ventilating all of your air through your oral cavity into the airflow transducer, and it'll be able to create a spirogram for you quite easily. It'll look something like this. I'll demo it for you, but just to go through the different volumes you gotta know. The procedure will ask you to breathe over time. Take 5 normal breaths. Just breathe into the thing. And it's very weird to breathe with a nose clip on, with on a mouthpiece, and you tend not to breathe normally, but just try. It's like it's kind of weird, and everyone's watching you. But just try to breathe normally. Do the best you can there. And it should look something like this when you take a normal breath. Breathe in, breathe out. That's like a breath. Take 5 normal breaths. In and out, in and out. 1, 2, 3, 4, 5. Then take a super deep breath in, then push it all out. Okay, so 1 super breath, max. They call it the vital capacity from top to bottom. And then follow it with 5 more normal breaths. That's it. It's really quick to get the data. So then you have to measure your volumes and your capacities. So those are shown on the table here. When you measure the tidal volume, it's just the volume of air doing normal quiet breathing. Pretty much from here to here. Okay. So that volume, I guess we'll call it number 1. TV, tidal volume. And you can look in the figure for the average values. About half a liter, 500 ml. And they give the averages for male and female. There's gender differences. On average, men weigh a little more, so they need a little more lung tissue to oxygenate their body tissue. So on average, male figures could be a little higher. Okay, let's see. So you can look at the description. The amount of air inhaled or exhaled with each breath under resting conditions. All right, so if you take a deep breath in, you have some reserve after a normal breath in. So that reserve is called, for a deep breath in, is the inspiratory reserve volume. And it will be the difference between this top value here and this top value here for your max breath in. So this volume of air is your IRV. Your inspiratory reserve volume, your IRV. Then, for your ERV, after a normal breath out, you can push out a little more, like when you gasp, push it all out. And, really strain to breathe in max and to breathe out maximally. Otherwise, your values won't make sense. You'll be like way off average, and you'll be asking me, how come we're not seeing the normal values? So you have to ask your subject, did they really give a max effort? So the ERV is the amount of air that can be forcefully exhaled after a normal tidal volume. 3 ERV. What you can do is just take the bottom value and then the bottom value of a normal breath out and measure that difference between these two. And that's your ERV. The most important one is the vital capacity, but before we get to there, there's something called the residual volume. It's like the difference between the bottom value that you can maximally do yourself with conscious effort, gasping all the air out of your lungs as best as you can. But the air that you cannot get out of your lungs because the lung wall is stuck to the chest wall is your residual volume. It's about 1 liter. There they say it's 1.2 liters. It's usually about 1 liter. It's RV, which stands for residual volume. It always resides there. You don't get rid of it unless you have a pneumothorax and your lung collapses. Of course, you don't want that to happen, but that's the residual volume. All right, so these volumes can add up to different capacities. The first one they have is total lung capacity. Okay, and they say on average it's about 6 liters for a man, 4.2 liters for a woman. It's the whole thing from top to bottom. So, in different color here. So from this top value, total lung capacity, everything, total. Vital capacity is the max one you can measure by voluntary effort. So it would be the value between this top value here and this bottom value there. And I think that's the most important one you measure, because you can measure it. We can only estimate residual volume, and we don't have the equipment to estimate that here today. But we can measure VC directly. So really give a max effort if you're a subject today, but you'll actually know your vital capacities. Fun knowledge for yourself, I guess. Okay, inspiratory capacity. It's all the air you're bringing in. So basically, it's the TV and the IRV. So you can just add them up or measure it directly. It's the TV, the IRV. It's basically from this bottom value here to this top value here, from there to there, all number 3. That's your IC, inspiratory capacity. It's all the air you're bringing in your lungs. 3 IC. That's it back there. Then the FRC, which I kind of lectured on already. FRC. So FRC is the end of a normal breath. All the air, the blue number 4, all the air that's in your lungs at the end of a normal breath. It's about 2-point-something liters, and like I said in lecture, it provides a mixing chamber for blood gases to exchange regardless if you're breathing in or breathing out, okay? And the point in lecture was FRC provides a reservoir so you can have steady state blood gases. Well, anyways, you can measure it, but you have to assume residual volume is about 1 liter, and the procedures will tell you how to do that. Okay, so those are the volumes and capacities we can measure in a spirometry lab, and you'll get to do it in 2 subjects. And the reason why we do spirometry is, there are pathologies that cause hypoxia, and you can indirectly measure them by using spirometry. So let's talk about some of the pathologies in the respiratory system. They kind of break down into 2 categories, restrictive or obstructive. Okay, let me read what I have for restrictive lung disease. As it's described, it is restrictive. The ability of the lung to stretch, like when you inflate it, we call that compliance. And compliance is generally a good thing. A high compliance lung stretches easily, so it's easy to inflate. A low compliance lung, a stiff lung, it requires more force from inspiratory muscles to stretch it. Diseases that decrease lung compliance are called restrictive lung diseases, and I'll mention a few. Ventilation is affected because more work must be expended to stretch a stiff lung. So basically, in this disease category, it's difficult to inflate a stiff lung. It's not compliant enough. The other major category of lung disease is obstructive. Normal quiet breathing resembles a nice whoosh. You shouldn't hear a person breathing. That's not a good sign. Diseases in which airflow is diminished because of increased airway resistance are obstructive lung diseases. When patients forcefully exhale, air whistles through narrowed airways, causing a wheezing sound that can be heard even without a stethoscope. Okay? In obstructive lung diseases, simply put, there is an obstruction. Typically, patients can inflate their lungs okay, but breathing out is kind of harder due to the obstruction. And in both cases, the concern is hypoxia, that you're not picking up enough oxygen in the pulmonary blood when you return it to the left heart. Okay. So let's go through some examples of lung disease. And then what they do is they show you, I have some pictures here of normal versus diseased lung. And what you should notice is in the diseases that blood is not fully oxygenated. And that's the main concern, that blood oxygen is not normal. So for emphysema, that is categorized as obstructive. In emphysema, there's a destruction of alveolar walls. It produces a smaller number of larger alveoli. Alveoli have less surface area. Lungs are overly compliant because you have a destruction of the elastic fibers. Okay, so when you inflate it, it inflates too easily, and without the elastic recoil, it's difficult to inflate. It's easy to inflate, it's difficult for the lungs to empty because of the destruction of the elastic fibers. Like, for example, in smoking, cigarette smoke can destroy those structural features. And so you get fewer, larger alveoli, and that's not good. There's not enough surface area. And you get a lot of stale air that's trapped in the lungs because lungs are difficult to empty, which contributes to the hypoxia. I showed you some pictures before, but here it is again, normal versus emphysema lung. What you can see here is normal lung on the left, and at the same magnification, it's quite obvious, the destruction of the alveolar spaces. And so emphysema produces a smaller number of larger alveoli, which is not efficient for gas exchange. This is what you want. Okay. Fibrotic lung disease is restrictive. In fibrotic lung disease, it's restrictive because it's characterized by this development of fibrous scar tissue that restricts the inflation of the lung. So it's too difficult to inflate that. So they show how thickened the alveolar wall is. The thickened respiratory membrane, it slows gas exchange, leading to the hypoxia again. Loss of lung compliance may decrease alveolar ventilation because it's difficult to inflate a stiff lung. Okay, you have pulmonary edema. Like, for example, you've got a cardiac patient whose left heart muscle is damaged, so they can't, fluids get backed up in the lungs and get this fluid build up in the lungs. You're increasing the diffusion distance for gas exchange because of the extra fluid. Therefore, it's you have hypoxia. It's considered restrictive. Put it over here. It's considered restrictive because it's hard to inflate a lung when there's fluid buildup around the alveolar spaces. For example, go home and try to blow up a balloon, but put the balloon underwater and see how hard it is. You probably can't do it because the pressure of the water on the balloon is blocking it from inflating. It's the same difference when you have fluid around your alveolar spaces. It restricts the lung from inflating. Asthma is obstructive lung disease. In asthma, the hypoxia is due to the constriction of the bronchioles. Usually there's a spasm of the smooth muscle, maybe due to some allergic or viral infection. And the increased airway resistance decreases the ventilation. So it's the bronchospasm that causes the problem there in asthma. Okay, so some pulmonary function tests that we can do. One is just minute ventilation. If you can measure the tidal volume per breath, and you get their breaths per minute, right? The average respiratory rate is something like 12 to 15 breaths a minute. You can calculate how much volume of air they're breathing per minute. Another one you can do is called FEV1, and this is one you're doing in lab today. FEV1 is important. This is called forced expiratory volume. So consider those first two words very carefully. The first one is forced. So if the subject is supposed to do it forcefully, that means as hard as you can, blow all the air out, because the second letter is E, expiratory. You're trying to measure how fast they can move air out of their lungs in 1 second. That's why it's FEV1. Okay? So if you just kind of do it lazily, it'll appear like you have lung disease. So that's why the forcefully is very important. How much air can you exhale in a second? So you first inhale all the way off the mouthpiece, then on the mouthpiece, blow it all out, all of it out. You'll blow out the most in the first second if there's no lung disease. And then the last 5, 6, 7, 8 seconds, you're just gasping every last millimeter of air out of your lungs. So it's not something that's done in a second. It takes many seconds. But you should be able to move most of it out in the first second. Okay. So this is seconds on the x-axis. 1, 2, 3, 4, 5, 6. You have to set it up so at time 0, you breathe out and it goes up the most in the first second because you're getting rid of most of the air in the first second, and then it kind of plateaus out, kind of like that. So I'll demo this, but basically, that top value, that max value, that's basically your vital capacity. Because you took a deep breath in, and then on the mouthpiece, you blew it all out. So it's your vital capacity. And we call it FVC, because again, the F is forced. The subject gave a maximal effort. And whatever that value is, that's your top mark. Maybe it's 4.3 liters. But then you want to measure how much they got out in the first second. So that value at exactly 1.0 seconds is FEV1. And let's say it's like typical value, maybe it's 4.1. So you blew out 4.1 of 4.3 in a second, okay? And so you calculate that as a percentage. You will sum percentage. The normal value should be 80%. In the absence of lung disease, you should be able to blow out 80% of your max. Okay, whatever that is, I don't want to. That's just an example. You could measure FEV3 or whatever, but we're just going to do FEV1. 80% is normal. 80% is normal. Write that down somewhere, and remember when you look at your subject. So that's one test. Okay, now here's a normal spirogram, like I drew to begin with. What it may look like for obstructive and restrictive, and how values may differ. For the obstructive, this is what it looks like. Lungs are easy to fill, but maybe they're difficult to empty. Like this wheezing, like you blow out through like a narrow straw. It's kind of like the airways are narrow due to the bronchoconstriction and spasming. So when you breathe in, easy, but when you breathe out, the slope of that is a little less steep. So air comes out more slowly. It's hard to get all the air out, so you have an increase in FRC, you have an increase in residual volume. There's less total lung capacity available for gas exchange. I would say this is the main thing you would measure is both vital capacity and FEV1 will drop, maybe less than 80% for the FEV1. If there's an obstruction, you usually see decreases in vital capacity and FEV1. For restrictive lung disease, there's no obstruction. So So FEV1 may appear normal because air is flowing freely. It's difficult to inflate a stiff lung, so the whole thing is like smushed. It's like, I would say the number one thing that you'll measure is vital capacity seems way reduced. If normal is 4 or 5 liters and 2.8, that's really low. Okay. So for restrictive, it may be that with a reduced vital capacity for restrictive. For example, I put a red line through FEV1 at 1 second. And obstructive on the top figure is the blue curve. And what you can see is that in an obstruction, there's no restriction. So you can eventually get all the air out. It just takes longer. So that in that first second, you should see a reduction. Normal is 80%. I mean, in obstructive, it could be much lower than that. In restrictive, you don't see a change in FEV1 because they can't even inflate their lungs all the way anyways. So FEV1 may appear normal, but their vital capacity is like much less than what it normally should be. Okay, in restrictive lung disease. So let me demo the lab real quick. We'll turn this off. So we're looking for L12 pulmonary function 1. Follow the procedure. Bam. Bam. Has me enter my age, 46, halfway to being dead. I'm joking. 5'8". So they got to know your age and your size, because that will determine like how much. It's a rough estimate on what your lungs need to do to oxygenate your blood, so they can kind of know. And what you can do is they ask you to do this. I'm going to emphasize this part because students tend to gloss over it. You know, you can predict someone's vital capacity, and there's all different kinds, there's charts and there's equations, because just based on your age and your gender and your height, you can predict. And so, the equation for females' vital capacity, this is on page 561 on the handout for looking at it. For female vital capacity, just predict it. You can use this equation. Height in centimeters. Age in years. Wait. I copied that wrong. 0.18. Mine is 2.69. That's for females. For males, if you want to predict a VC, it is 0.052. All right, so for the height, it's got to be in centimeters. So, 68 inches. Know that there's 2.54 centimeters in an inch. So I'll figure out my height in centimeters. Uh, 172.72. Age in years, I believe. 26. So these are my parameters. You plug it in, the male category. So what you do is you multiply, make sure it comes out right here. My predicted VC is 4.368 meters. So let's do it and see how close to predicted it gets. Calibrate. Okay, let's set it up. That goes in channel 1. Be careful with our equipment. This is very expensive. Plug it in the right channel. Channel 1. Remember, follow the screen instructions. Sometimes they change the procedures and they don't update. Pearson doesn't update it. So the procedure is still good, but if there's something that's off, go with the on screen as the default to be correct. All right, so I'll get that. We're going to calibrate first. What you got to do is this has two sides. We're going to use both of them, but normally you use the side that says inlet. That's the side you put all the equipment on. If you're just calibrating, what you got to do is set it up just like the person is breathing, and you have to use the filter with the syringe. These are one-time use. You can throw out the nose clip, the mouthpiece, and this filter when the subject is done. So again, start with, put it on the side that says inlet. And then the syringe fits nice and snug right through there. Okay. The it's good to start with the plunger out. So this is the correct setup. And it's very important to kind of put both hands on the syringe. The mistake students make is like you want to grab it by this handle. That is really bad, because what you'll do for sure is you'll put tension on this lip here and you'll crack it. And we've busted every single syringe at one point because students aren't listening to me right now. Is this right?
No.
Is this right?
Yes.
Yes. Okay. Good. Don't break our equipment. We don't like it. I wish we could make you pay for it if you broke it. That would you'll do it right. But anyways, we don't hold you responsible because you're just students. We'll foot the bill. But do it the right way in my class. How about that? Let's calibrate here. The first step, just hold it still. See that blue line going across the string? Just let it be, this is like a 0 point. Just do nothing. Okay, compare it with the example data on the bottom there. Then you can continue. And read the bottom. So during calibration, you're going to do 10 strokes, in and out 5 times. That's 1, 2. It doesn't look quite like that. I don't know why they make the data look like that. It always looks like I just did it. So what I did was good. So I'm going to continue. Okay, so now you can remove the calibration and use the subject. So the only thing to add to the filter is the mouthpiece. And the nose clip. There's the mouthpiece. So remember the procedure. Nose clip on, then 5 normal breaths, super deep breath. 5 normal breaths, done. So you see how I did that? Was it obvious when I did my vital capacity?
Yes.
And it should be obvious when you're subject. I always demo it because I remember the first year I did this, people weren't doing it right. It's like, you're not going to get any good data out of that. You couldn't even see the vital capacity. So you have to give a max effort, okay? Straight, otherwise the data is going to be off. Oh, that looks okay. I'm going to go done. Okay, so you're done, yeah. Spirogram should look like that. You can measure your values. I'll just go ahead and look. There's different values. There's P to P, there's max, there's all these different things. Okay. Peak to peak, look at that. That value is whatever you highlight, it takes the difference between top value, bottom value. So look how I've highlighted it. Top value, bottom value. Okay, so if I look from peak to peak, that says 3.84 liters. So that's my actual VC. It's a little off from my predicted because, this week actually I had been problem with my allergies. I woke up this morning, I was wheezing. So I'm not surprised that, I'm about a half liter lower than possible. And normally when I do this every year, I get really close to my predicted. Okay. So that's why it's good to do predicted versus actual. The other things you can measure, for example, if you have to measure IRV, look what I've highlighted. I want to measure IRV. IRV is the difference between this top value and this top value. So to do that, I would look at delta. Delta's right here. Delta is basically it subtracts the beginning and the end. Okay? It's not peak to peak. Peak to peak is top and bottom, right? Top, bottom. But that is not IRV. Peak to peak is 3.01. That's my IC, but I want IRV. I just want this one and that one. So my IRV is 2.21. That sounds more correct. Okay, the other one that you got to do is ERV, and that's the difference between look what I highlighted. I want to do ERV. It's the difference between this bottom value and that bottom value. If you look at delta, that'll give you the right thing. It just takes the difference between the first and the last. It's not peak to peak. So that's about 0.85 liters. Yeah, that's about right. About a liter is right for ERV. Okay. And so, let me see if you're with me here. What am I trying to measure now? By what I highlighted, what do you think I'm trying to measure? TV. The difference between this value and that value. You can go peak to peak. It's about a liter. Typically, it should be 500, but it's always a little more because it's so abnormal to try to breathe through that thing. So, yeah, this looks about right. So, that's the basic idea for a spirogram. There's another thing I want you to do. It's the FEV1. But basically, if you look at the data tables, you got to do that twice for both subjects and look at the tables that I have there. Make sure everything is filled out. Make sure you answer everything. If you leave anything blank, points are coming off. It's page 6. There's this picture here. What you got to do for vital capacity. See, normally when you breathe out, it goes down. But I would like it by convention to go up when you breathe out. So you have to switch the mouthpiece for FEV1. So what you got to do is just start over. Let's make me calibrate again. Okay, well, we can do that again. it's letting me do it now. Okay, let's remember, I would like you to move the mouthpiece to the other side. So it'll look like the FEV curves I showed you before. So for FEV1, I take a max breath in off the mouthpiece and just breathe it all out on the mouthpiece. Okay. I'll wake you up. Something that looks like that. Oh, well, dang it. What happened? Mistake you guys made. Very good. Okay. All right, so what you got to do for time 0, you have to set 1 to delta t. Because FEV1, what's the 1 stand for?
1 second.
1 second. So you got to figure out where time 0 is so you can figure out what 1 second is. On a graph that looks like this, I started to breathe out right here. Okay, so you don't eyeball it. Use the delta t function. Look over here. I want you to just click and drag until that reads 1.0 from time 0, which is right there. So here's how you do it. I'm looking at delta t. Boom. That's 1.0 seconds exactly. And what you can do is you want to measure this value right there. So you can just read from max, because max gives you the max value within what you're recording. This says 3.14. So yeah, go from here. And I'm asking you to kind of sketch out your graph. And pay attention here, because this is where typically groups lose points. You don't give me enough information on your graph. When you make a graph, let's be reminded of what it needs to be included. There's X and Y axis. Volume is on the X axis. That's going to be liters, and it's time in seconds on the Y. So on the X axis, time in seconds, and then boom here. And then what you do is kind of looks like that. Just to give a rough sketch. So that's time 0, and I'm measuring out till it looks like 1.0. And that first value that's going to be my FEV1. Okay, and when you read from max, 3.15 just around. But I want the top value. The top value is right in here. So an easy thing to do is just to highlight that whole top of the curve and just read from max. The max value I gave is I pushed 3.48 out. This value here. That's my FEC. I said 3.4. Yeah, okay, that's cool. Well, anyways, what you need to do is take the percentage, part divided by the whole, right? Times 100. Should be 80% if it's normal. That's 90.5%, so it's within the normal range. What I would like you to do is be sure you label it like I did with all the values. FEV1 and FVC need to be clearly indicated on your graphs to, well, not lose points. Let's take a break, and when we come back from break, we'll go right into lab.